Hello and welcome to today's talk. Today we'll be talking about load balancing under strict compatibility constraint. My name is Daan Rutten. I'm a PhD candidate at the Georgia Institute of Technology in Atlanta, and this is a joint work with Debankur Mukherjee. So a typical model for load balancing in large-scale systems is the following. We see a dispatcher. Tasks arrive at the dispatcher, and as soon as they arrive, they're routed to one server. At the server, each server has an individual queue where the tasks wait until they're being served by the server. The question we're concerned with today is the compatibility constraints between the dispatcher and the server. And the question we would like to answer today is the following. How do we design an appropriate compatibility structure such that the system has the same asymptotic performance as a fully flexible system? Fully flexible here means that each dispatcher is actually able to route a job to each and every server. Today we'll see that actually much sparser compatibility structures, sparser than a fully flexible system, are actually able to enjoy the benefits of a fully flexible system. We do, however, need to create an appropriate condition, and this condition will also be satisfied if the graph is actually suitably random, such that this performance actually holds. So what are compatibility constraints? Well, in practice, you usually have compatibility constraints. For example, if you have two different types of queries, a Google search query and a Google Maps query, they typically require very different data from the server. Maybe there are even specialized servers to be able to handle those different tasks. And it's actually infeasible to design a system where each server would be able to handle this vast number of different tasks. There are overwhelming implementation costs. Maybe the system is even geographically constrained to only handle certain task types. However, typically the research community assumes full flexibility. They do that because then the system becomes analytically tractable. However, today we introduce an approach such that we can also analyze systems that are not fully flexible and actually have compatibility constraints. Our model is the following. We see M dispatchers at the top. They each get tasks from a Poisson arrival, and they route their jobs to one of the servers. We have N servers on the bottom, and each server handles the jobs at an exponential rate of 1. So we have exponential arrival, exponential service times. There is a bipartite graph between the dispatchers and the servers. If there is an edge between a dispatcher and a server, it means that they are compatible and a dispatcher can send the job to this server. If there is no edge, they're incompatible, and the dispatcher is not allowed to send a job to this server. We have a total arrival rate in the system of lambda n, and lambda is strictly smaller than 1. We'll look at the large-scale system. So that means that both the number of servers and the number of dispatchers will go to infinity. Also, the algorithm we use to route jobs to different servers is the JSQD scheme, or the supermarket model. That means that if a job arrives, then the dispatcher will select D random queues at random. And out of those D sampled queues, it will select the shortest one, and the job will be routed to that queue. This D is a constant, for example 2, throughout the talk. So our goal is the following. What is the minimum sparsity in our bipartite graph Gn, such that we have the same asymptotic performance as a fully flexible system? A fully flexible system is a complete bipartite graph. So one of the challenges that comes with this kind of analysis is monotonicity. It turns out that the system is non-monotone with respect to edge addition. So if you create a more flexible system, if you add more edges between dispatchers and servers, it turns out that it can actually harm performance. And this is an example of this. Here we see a simple system that is actually stable. However, if we add more edges, so if we let every dispatcher be connected to server 1 and 2, we'll see that server 1 and 2 will actually receive way more jobs than they are able to handle. For example, if you take DS2 and you work out this example, you see that each dispatcher has a non-zero probability of routing a job to either server 1 or 2, which will overload these servers. Today we'll tackle this problem. In fact, we have the following contributions. First of all, we introduced a sufficient expansion property on a sequence of graphs. This is a novel condition that has been seen before. Under this condition, we show both process level limit and convergence of the steady state of the system. Furthermore, we also show how you can actually construct graphs that satisfy our expansion property. It turns out that if you construct your graph to be suitably random, then it will actually satisfy these process level limit and steady state convergence. So in short, we show that much sparser compatibility structures may enjoy the same benefits as a fully flexible system. So a high-level approach is the following. We look at deterministic sequences of graphs that satisfy our condition, and we show that our properties are satisfied. For the random graphs, we actually use a concentration of measure arguments to show that they satisfy our condition almost surely. And that also implies that they satisfy the limit class. Today I'll mainly focus on the process level limit and the deterministic sequences. We'll briefly touch on how to construct a graph that is suitably random, but due to the length I can only focus on the process level limit. The paper of this talk is actually on arXiv, so feel free to have a look at that if you're interested. So what is this expansion property? We call it proportional sparsity, and it's the following condition. Note that we have one new notation, NW is the set of neighbors of a dispatcher W. Then this is our condition. It says that the sequence is proportionally sparse if for each epsilon this condition holds. And we see two terms here. We see NW intersected with U, where U is a set of servers, and we see U over N. The left term is actually the number of servers in the neighborhood of W, and then as a fraction of the number of servers in the neighborhood. That should be approximately equal to the size of this set, U over N. So let's see an example of that. So here we see U is 3 servers. We have 6 servers in total, so that means that U over N is half. So W, it's one dispatcher, will satisfy proportional sparsity if the number of servers that is connected to W as a fraction of the total number of servers that W has in its neighborhood is actually half. So here we see that it actually satisfies proportional sparsity. We see that 1 out of the 2 servers is connected to U. So again, that's a half. This proportional sparsity property is actually related to a well-known graph property called quasi-randomness. We show that quasi-randomness actually implies proportional sparsity. The other way around is not true, so that means that proportional sparsity is a more general property than the earlier notion of quasi-randomness. So under this condition, we prove a strong result, the following result. If a sequence of graphs Gn is proportionally sparse, then we show that Q, and Q is the fraction of servers with Q length larger or equal than I, converges to this system of ordinary differential equations. This system of ordinary differential equations is actually a description of the fully flexible system. So that means that as n tends to infinity, the performance of our system actually coincides with the fully flexible system. And this Q vector is actually a common measure for the performance, the Q length. So it relates to waiting time, for example, average waiting time of a job. So our proof the high-level idea of our proof is the following. We show that from the perspective of a dispatcher, the local queue-length distribution, so the queue-length distribution in its neighborhood, is uniformly close in L1 distance to the global queue-length distribution. Secondly, we construct an optimal coupling, a novel coupling between our sparse compatibility graph Gn and the fully flexible system. The problem here, one difficulty here is that a dispatcher W might actually have a different set of compatible servers in both systems. So what we do is we couple only the queue lengths of the servers and not the actual index of the servers. Third, because we showed one and we look under this optimal coupling, we know that the probability that a task is routed to different queue lengths will actually become very small. And it will actually become so small that the performance of these systems is equal. And that's exactly what we wanted to show. So how can we construct graphs that satisfy this expansion property? Well, here's an example. So here, typically the degree of a server, so the number of task types that is able to serve, is related to the storage capacity or the complexity of the system. So what we do here, let's say each server has a fixed degree Dn. What is the minimum growth rate of Dn necessary to have the same performance as the fully flexible system? It turns out if we do this randomly, then we can easily proportional sparse graph sequence. So here's the theorem that says this. So let's say each server selects Dn types at random of all the dispatchers. Then we actually see proportional sparsity if Dn grows large enough. So Dn should grow to infinity and should also grow proportionally to the logarithm of n over n. If it satisfies this property, then we see that it is proportionally sparse, and it also satisfies the limit laws. So in conclusion, what did we see today? Well, we analyzed the supermarket model for large-scale systems with sparse compatibility graphs. If we look at the last slide again, we see that there is a very, very slight condition on the degree. For example, the second one only says that the degree should grow to infinity at any rate. That means that it's much, much sparser than the fully flexible system, where the degree is n, the number of servers. We also show that these compatibility constraints actually have the same performance benefits of a fully flexible system. We need the graph to be sufficiently random to actually satisfy our condition to be able to show this. Thank you for your attention, and I hope you enjoyed this talk.